Okay, in this lecture, we want to talk about our operators and put them to use. And this will get us to the heart of quantum mechanics, but we're going to take a little bit of a side route here and revisit Maxwell's wave equation, which we discussed before. So recall this is the form here, that this second order partial differential equation. And we talked about solution. Here we're writing in terms of psi. We will change that. Let's just think of that as the E field component, but we're eventually going to change it to be something else. But it's just a function that satisfies that equation. We want to write it in the suggested form of breaking out those two derivatives of time and position as two separate. And what that does is allows us to go back to the previous lecture and recognize that it's really just two applications of our P and E operators, our momentum and energy operators. So recall that we had P is equal to minus IH bar partial partial X and E is equal to IH bar partial partial T. What we can do is just manipulate this equation, multiply through by IH bar quantity squared, which is also equal to minus IH bar quantity squared, so that we can write this in terms of the operators. So we get an operator equation. And when we do that, it takes a few steps and goes as follows. So we first of all, we multiply through by the here minus IH bar squared. And in this term, we multiply through by IH bar squared. Those are equivalent. And notice that in the parentheses here, I have two forms of E, and here I have two forms of P. So I can just immediately express those in terms of the operators, remembering they act to the right. So I can write it as follows. Now, we use the convention, which is should be pretty obvious, that when we act P on a function, and then we act on it again, the same one, we could just call that P squared. So P squared implies that we operate once with P, and then we operate again with result of that. And so we can rewrite the equation as follows here, and then we bring it to the other side, multiply through by C squared. We get this formula here. It might start looking something familiar, but let's play with it a little bit. But to do this, what we want to do is recall that these, we're going to assume here, this is the assumption here, that psi, that function psi, is in an eigenstate of energy and momentum. With that in mind, we can write P, the operator P acting on psi as P psi, just the momentum, and E's E psi, the energy, the scalar E. That way we can write this equation, which we had from before, just in terms of the eigenvalues, that is, which are the definite values that the state is in, E and P. And now we can see, well, okay, now there's no longer any operators in this. We can divide psi on both sides of the equation and take the square root, and we get E is equal to PC. And we recognize that from our relativity portion as the energy of a photon, a massless particle. So that tells us that what we have, a tie between the wave equation and the energy for this object in this case. So in this case, the relativistic energy for a photon is E equals PC, and it gives a direct tie-in to the wave equation. So we see there's a connection there. And that connection will allow us to extend to other objects to develop wave equations in unusual or unfamiliar territory, which is the goal here. So what I want to do is list out the process of which we followed here, but go backwards, say, because what we're going to start with, we're going to know the energy expression, and we want to kind of work this process backwards to see how we can, quote unquote, derive a wave equation. It's not formally a formal derivation, but it is a way to suggest heavily what the wave equation should be. So here's the process, and again, we're going to write this, in terms of the Maxwell's wave equation for now, we just think this. So I'm going to just go backwards from what I did in the previous screens. So we start with the classical energy for a particle. And then there is this item 2 here is a caveat that if P is an odd power, we need to square the equation, or to make it somehow make the power of P even. So we need that. That's just one technical point, which we're not going to get into at the moment. Then you just multiply both sides of the equation by psi, multiply it by on the right. And again, psi is assumed to be an eigenfunction of energy and momentum. That's a big assumption there, but we're going to assume that for this as follows. And now we can just go backwards and use the operator expressions to write the eigenvalues of P and E that are occurring in the energy expression in terms of the operators P and E. And then what we do is now we substitute the differential forms for these operators for P and then simplify. And then make it into a clean looking formula that we like. And that will give the quantum wave equation for the object represented by its wave function. That's the process we're going to follow in the next lecture. So it's a very straightforward process. Now, this was done. This is, again, getting at the beginning of quantum mechanics. And Schrödinger did this in the mid-1920s, 25. And what he did first, he considered an electron. And so an electron is usually the item that we're interested in. If you're talking about, say, a hydrogen atom, it's one of the first significant systems you want to kind of analyze. Anyways, but he obviously is, this 1925, started with the relativistic energy. E is equal to square root mc squared quantity squared plus p squared c squared. So first of all, we see a problem that how do we deal with operators under square roots? Well, you just square it. And he derived an equation from that, but it's not called the Schrödinger equation. It's actually called the Klein-Gordon equation, which is of use later on in quantum field theory. But he did this, but when he did this, he came up with some problems. Recognized that his probabilities weren't normalized. Essentially, the scenario is basically, say you send a single particle and have it impinge on a potential barrier. Usually you'd get a probability that some's transmitted and some's reflected. When he did that, he found he couldn't normalize the probabilities. And later it was seen that essentially what's happening there is that you're sending in one particle and you're coming out with more than one particle. So you can't normalize it in terms of a single particle theory. So what he did is he didn't understand that at the time, but what he did is he went back and then said, okay, well, let's not look at the relativistic expression. Let's just deal with the classical expression. So he went back to our classical energy of E is equal to kinetic energy plus potential energy and derived an equation there. And that is what's called the Schrödinger equation. And we will look at that in the next lecture.